Let's take a look at polyelectronic atoms now, rather than hydrogen. Not only is there uncertainty now about the electron position, but we also have to worry about other electrons interacting with the one that we're looking at. Helium atoms, compared with helium plus 1 ions, they have the same nuclear charge. Both of them have 2 protons. First ionization energy for a helium atom is 2372 kilojoules. When we go to rip off the second electron from helium, we get a much bigger ionization energy. The reason these are so different is we have the same nuclear charge, but we have electrons repelling each other when we're dealing with helium atom, and we have only one electron that doesn't have anything to repel it when we're looking at the helium ion. What this means is electrons in atoms repel each other, and that effectively lowers the nuclear charge, or the pull that the electrons feel from the nucleus. This pull that each electron feels is called the effective nuclear charge, and we label it Z effective or Z sub-effective. And we can figure out the effective nuclear charge for any electron in an atom by taking the nuclear charge, the Z number, which is the number of protons, and subtract any repulsive effects that electrons have on the electron we're studying. Now if we go back to our delta E equation, looking at the amount of energy necessary to rip an electron off, that gives us a measure of how tightly bound the electrons are to the atom. So here's our ionization energy equation again. Z effective rather than Z squared over N squared allows us to determine our ionization energy. Remember, the 1312 kilojoules per mole is the amount of energy it takes to rip the electron off of a hydrogen atom. If we know the ionization energy for a particular electron, for a particular atom, we can work backwards and we can figure out that Z effective value for the electron. If we take a look at sodium, the ionization energy for the third S electron, so the outermost energy shell electron, is 495 kilojoules. It's fairly small because that electron's pretty far from the nucleus. Plus, it has 10 electrons between it and the nucleus. So those electrons are all repelling that outer one. They're also shielding that outer one from the pull of the nucleus. Ionization energy, on the other hand, for the 1s electron, so the electron closest to the nucleus, is a little bit bigger, 1.39 times 10 to the 5th kilojoules per mole. So the effective nuclear charge for the 1s electron, the electron closest to the nucleus, is 10.3. The effective nuclear charge for the 3s electron, that outermost electron, is 1.84. You might think that it would be smaller. You might think the effective nuclear charge for the 3s electron would be 1, because there are 10 electrons between it and the nucleus. It's a little bit bigger than that. You also might think that the effective nuclear charge for the 1s electron, that electron closest to the nucleus, should be closer to 11 rather than 10.3. Let's take a look at why those aren't the case. So that 1s electron is closer to the nucleus. It's only shielded by one other electron, the other electron in the 1s orbital. And so those two electrons are going to repel each other in addition to being pulled by the nucleus. So their effective nuclear charge is actually smaller than 11, but a little bit bigger than 10. The 3s electron has a very low ionization energy. As we said, it's shielded by those inner electrons. And so those electrons are going to repel the 3s electron, as well as shielding it from the nucleus, so the nuclear pull isn't felt as strongly. If 10 electrons completely effectively shield the 3s electron, then the Z effective should be 1. It isn't. So that 3s electron doesn't spend all of its time out in that third energy shell. The 3s electron can actually move to energy shells closer to the nucleus. It's called penetrate closer to the nucleus, goes to the 2 or the 1 energy levels. When it does that, it has a higher effective nuclear charge. So what that does effectively is the average nuclear pull that the 3s electron feels is not 1, but 1.84. If we look at this top graph, we have the 1s radius. It's about 50 picometers. This is, again, the psi squared of the probability distribution of where that electron is found. So if you take a look, that 1s electron can actually end up closer to the nucleus than the 1s shell. It can also exist further away from the nucleus. 2s and the 2p orbitals are also shown. 2s orbital is actually a little bit bigger than the 2p orbital, 2p orbital being in yellow, the 2s orbital being the pink one. The other thing that we see with the 2s orbital is this one right here, is electrons most of the time hang out right around 280, 288 picometers, but they can also exist in, it's essentially the 1s orbital, and that's why there's a bump down there. It's because electrons in the 2s most of the time spend their time in one place, but can spend their time in other places. Okay, if we look at this set of graphs, it gives us a little bit different picture of what's going on. The top set of graphs are the s orbitals. The second set of graphs are the p orbitals. The third set of graphs are the d orbitals. So if we take a look at our 3s electron for sodium, it hangs out here most of the time. Sometimes, however, it can hang out here, which is about the same position as the 2s orbital. It could also sometimes hang out here, which is approximately the same position as the 2p orbital. It's a little closer than the 2s to the nucleus. That electron can also hang out here, which is approximately the same position as the 1s orbital. When that 3s electron hangs out in orbitals closer to the nucleus, it has a stronger effective nuclear charge, and so that gives us an overall higher Z effective for that electron as opposed to 1.